Orientation on a n-surface in Rn plus 1. Last theorem we have discussed about the smooth unit normal vector fields on a connected n-surface. That is, if S is a connected n-surface in Rn plus 1, then there exists exactly two smooth unit normal vector fields. If S is not a connected set, then we can't say anything about the existence of such fields. And for an arbitrary n-surface S in Rn plus 1, if there exists such a vector field, that is, if there exists a smooth unit normal vector field on S, then that vector field is known as orientation on S. That is, a smooth unit normal vector field on an n-surface S in Rn plus 1 is called an orientation on S. And an n-surface together with the choice of orientation is called an oriented n-surface. That is, if there exists such a vector field on S, then S is known as oriented n-surface in Rn plus 1. By last theorem, we can say that any connected n-surface in Rn plus 1 is a oriented n-surface in Rn plus 1. Next, consider Mobius band. A Mobius band is a structure in R3 which is not orientable, and it is obtained by taking a rectangular strip of paper, twisting one end through 180 degree and tapping the ends together. That there is no smooth unit normal vector field on B, because consider the central circle of this Mobius band, and by picking a unit normal vector at some point on the central circle and trying to extend it continuously to a unit normal vector field along this circle. After going around the circle once, we can see that the normal vector is pointing in the opposite direction. That is, if there exists a smooth unit normal vector field, we by approaching through this circle, we can see that there is after one rotation, the normal vector is pointing in the opposite direction. Hence, we can say that there is no smooth unit normal vector field on B. Since B is a connected structure in R2, if it is a two surface in R3, then B Mobius band will be a connected two surface in R3. Then by last theorem, we can say that there exists exactly two orientation on this Mobius band. So, since B is not orientable, we can say that B is not a two surface in R3. Hence, we can say that B cannot be expressed as, that is, the Mobius band cannot be expressed as a level set F inverse of C of some smooth function F from U to R with del F of P not equal to 0 for all P belongs to S, and hence B is not a two surface in R3 and it is known as unorientable two surface. A unit vector in Rpn plus 1 is called a direction at P. Now consider a oriented n-surface in Rn plus 1. Then by using its orientation, you can find the theta rotation and handedness of vectors in tangent spaces. For that, next we are going to discuss about these topics. For that, let C be an oriented plane curve in R2. That is, let C be an oriented one surface in R2. Then the direction obtained by rotating the orientation normal direction at P through an angle minus pi by 2 is called positive tangent direction. That is, positive tangent direction is the direction obtained by rotating normal direction through an angle minus pi by 2. For an example, consider the function f from R2 to R defined by f of x1 x2 equal to x1 square plus x2 square. And let C is equal to f inverse of C. Then C is a unit circle centered at 0 and with radius root C. Here f is a smooth function and del f of P is not equal to 0 for each point P on the circle. Hence, C is a one surface in R2 and it is orientable also. Now consider this circle together with this orientation. That is, in this orientation, the orientation, consider the circle together with the orientation which maps each point in C onto the unit vector which pointing outside of this circle. Then by direction, positive tangent direction can be obtained by rotating this normal direction through an angle minus pi by 2. That is, it will be the positive tangent direction in this case. And consider the same circle together with this orientation. That is, consider the circle, the orientation that maps each point on this circle onto the unit vectors which pointing inside of this circle. Here in this case, it will be the positive tangent direction at this point. Now, next, let S be a two surface in R3 with an orientation N and fix P belongs to, fix some point P in R3. Here it is R3. For each theta belongs to R, define R theta from SP to SP by R theta of V equal to cos theta V plus sin theta N of P cross V. Then R theta is called positive theta rotation at the point P. Here V is a vector in Rp and V equal to PV and N of P equal to Pn of P. Next, let S be a three surface in R4 with an orientation N where N of P equal to Pn of P for each P belongs to S. Then an ordered orthonormal basis E1, E2, E3 of SP is said to be right-handed if the determinant E1, E2, E3 N of P is greater than 0 where EI equal to PEI for each I equal to 1, 2, 3. And if this determinant is negative, then we say that the ordered orthonormal basis is left-handed. That is, if this determinant is positive, then the ordered orthonormal basis is right-handed. And if this is negative, then the ordered orthonormal basis is left-handed. Next, by using this orientation, we can say about the consistency of an ordered basis of SP in an arbitrary space. For that, let S be an n-surface with an orientation n, where N of P equal to Pn of P for P belongs to S. Then an ordered basis V1, V2, etc. Vn of SP is consistent with the orientation if determinant of V1, V2, etc. Vn n of p is greater than 0, where vi equal to pvi for I equal to 1 to etc. n. And if this determinant is negative, then we say that the ordered basis is inconsistent with the orientation. Next, consider this question. Rn may be viewed as the n-surface xn plus 1 equal to 0 in Rn plus 1, and let n be the orientation on Rn, which is a subset of Rn plus 1, defined by n of p equal to p 0 0 etc 0 1 for each p belongs to Rn. This orientation is called natural orientation on Rn. Show that given this orientation for each n, the positive tangent direction at p belongs to R1 is the direction p10, and the positive theta rotation in Rp2 for p belongs to R2 is counterclockwise rotation through the angle theta. And also show that the ordered orthonormal basis, this orthonormal basis for Rp3 for p belongs to R3 is right-handed. Here Rn is the n-surface xn plus 1 equal to 0 in Rn plus 1. Consider the function f of x1, x2, etc. xn plus 1 equal to xn plus 1, which is defined on Rn plus 1. Then this set Rn, this n surface Rn is equal to f inverse of 0. And del f of p is equal to p dou f by dou x1, dou f by dou x2, etc. Dou f by dou xn, dou f by dou xn plus 1. Here it is equal to p 0 0 etc 0 1, because dou f by dou xi equal to 0 for each I equal to 1 to etc n, and dou f by dou xn plus 1 is equal to 1. Hence del f of p is not equal to 0. So Rn is the one surface corresponding to this function f. And first we want to show that the positive tangent direction at p belongs to R1 is the direction p10. Here R1 is equal to f inverse of 0 for f defined on for f of x1, x2 equal to x2. N equal to, here it is the case n equal to 1, and n of p equal to p0 1. We need to show that the positive tangent direction is obtained by rotating n of p. Here we need to show that the positive tangent direction is equal to p10, and we know the positive tangent direction is obtained by rotating n of p by an angle minus pi by 2. Also we know that if we rotate a point xy in R2 by an angle theta, then the resultant vector x dash y dash in R2 will be equal to cos theta minus sin theta cos theta into the matrix xy. Then the vector obtained by rotating n of p equal to p0 1 by an angle minus pi by 2 will be equal to px dash y dash, where x dash y dash is equal to cos minus pi by 2 minus sin pi by 2 sin minus pi by 2 cos minus pi by 2 into the matrix into 0 1, which is equal to 0. Here cos pi minus pi by 2 is equal to 0, and minus sin pi by 2 is equal to minus 1, hence it is equal to 0. 1 minus 1 into minus 1, it is equal to 1. So it is equal to 0, 1, minus 1, 0 into 0, 1. And by multiplying these two matrices, it is equal to 1, 0. So the positive tangent direction at P belongs to R1 is the direction P1, 0. Next we want to show that the positive theta rotation in RP2 is counterclockwise rotation through the angle theta. For that, here it is the case when n equal to 2 and here n of p equal to p0, 0, 1. By definition, r theta of v equal to, that is theta or positive theta rotation is equal to cos theta v plus sin theta into n of p cross v, and it is equal to cos theta pv plus sin theta into p n of p cross pv. If v equal to v1, v2, v3, then n of p equal to v, n of p cross v equal to n of p cross v, and it is equal to determinant of the matrix I, j, k, 0, 0, 1, v1, v2, v3, and it is equal to minus v2 minus v1, 0. Hence, r theta of v is equal to cos theta p v1, v2, v3 plus sin theta p minus v2 minus v1, 0. And it is equal to p cos theta v1 minus sin theta v2 cos theta v2 minus sin theta v1 cos theta v3. That is by rotating, that is the vector obtained by rotating this vector v1, v2, v3 through an angle theta is equal to cos theta minus sin theta 0 minus sin theta cos theta 0, 0, 0 cos theta into v1, v2, v3. By putting positive values for theta, you can see that this is in counterclockwise direction. That is, here by putting the positive values for theta, the rotation, you can see that the vector is moving in counterclockwise direction. Hence it is in counter. Hence here the positive theta rotation is in counterclockwise direction. In general, positive theta rotation is always in counterclockwise direction. Now, next, at last, we want to show that the given orthonormal basis is right-handed. For that, consider E1 is equal to P1 0 0 0, E2 equal to P0 1 0 0, and E3 equal to P0 0 1 0, and n of p equal to P0 0 0 1. We know that by definition, an ordered orthonormal basis is right-handed if this determinant is greater than 0, and left-handed if this determinant is less than 0. So consider the determinant of that matrix. When we consider the determinant of that matrix, it is equal to this. Here it is E1, E2, E3 and n of p. And determinant of this matrix is equal to 1, which is greater than 0. So the orthonormal basis is right-handed. In this video, we were discussed about orientation on a n-surface and discussed about Mobius band. Mobius band is a surface in R3 which is not orientable. And we said about theta rotation, positive tangent direction, handedness, consistency of ordered bases, etc. And Also we discussed about discussed some problems, one problem, and you need to prepare note on this video, about this video, on the topic in this that we discussed in this video, and need to submit very next day.